Welcome to the second video of Chapter 4. If you remember from our first video, Chapter 4, or this third unit, is going to cover all things linear differential equations. Our first video covered a lot of background and vocabulary. We looked mostly at homogeneous linear differential equations, and we took a sneak peek at non-homogeneous. We talked about linearly independent and dependent solutions, the Wronskian, the superposition principle, and we used all of that to take a sneak peek at constructing the general solution. So what we're going to do today is a process called reduction of order. So at the top, let's start with what is reduction of order. Suppose that we have y1, which is a non-zero solution of a second order linear differential equation, and this one's homogeneous because it's set equal to 0. Reduction of order is a process we use to find a second solution by reducing the order from second order to first order. So the best way to see this is just to go through the process. So this is example 1. Given y is equal to x cubed is a solution of that second order equation. Use reduction of order to find a second solution. Step 1. You are going to let y be equal to u of x multiplied by the solution that we already know, which is x to the third. So this is always the same, and that is the known solution. Okay, going to our equation, we know we're going to need a second derivative. So first thing we're going to do, or next thing we're going to do, is we're going to differentiate that expression that we have above. So we get u prime of x times x to the third, add 3x squared times u of x. We're going to need the second derivative in our equation. So doing that, we get 3x squared times u prime of x, add u double prime of x times x to the third, add 6x times u of x, add u prime of x times 3x squared. And if we simplify that, we get y double prime. Now, just to make things a little bit easier for me, from now on, instead of writing u of x, I'm just going to write a u. So I'll get 6xu, keeping in mind that u is a function of x, add 6x squared u prime, add x cubed u double prime. Okay, so now what we're going to do is we are going to return to our differential equation. So we're going to return to this equation, substituting in that y double prime and the y. So x squared y double prime, subtract 6y is equal to 0. If we substitute in, we get x squared. That y double prime from above is 6xu. Add 6x squared u prime. Add x cubed u double prime. Subtract 6. And then our y was just u times x cubed is equal to 0. Okay, so we're going to notice doing a little simplifying. When we distribute that x squared, those two terms are going to subtract out to be 0. So we just have these terms left with that x squared. So that simplifies then to x to the fifth, u double prime, add 6x to the fourth, u prime is equal to 0. Okay, so at this point, we're going to have to do some substitution again. What we should be looking at or noticing is that this u double prime is the derivative of this one. So we're going to substitute again. Noticing that u double prime is the derivative of u prime, what we can do is we can say, let's introduce another variable w that's u prime. Then dw will be u double prime. Okay, so we substitute that in. And when we do, we get x to the fifth dw, add 6x to the fourth times w equals 0. We want to put this in standard form, so we're going to divide by x to the fifth. So that dw I can also write as w prime. Add 6 over x times w is equal to 0. Now our equation is the form that we know how to solve. So we're going to have to remember back to all those solving methods. We can either treat this as a linear equation, or we can solve by separation. I'm going to treat this as a linear equation. So finding our integrating factor, we're going to have e to the integral of 6 over x dx, which is e to the 6 natural log of x, which is x to the 6th. So then going to our equation and multiplying by x to the 6th, we have w prime adds 6 over x times w equals 0. We multiply by x to the 6th. When we do that, on the left side, we should have x to the 6th times w, the derivative of that product. And then if you remember, we're going to integrate. So we get x to the 6th times w is equal to c1. Okay, and now we're going to have to do that process of going backwards, resubstituting things. So we know that w we defined as u prime. So I'm going to continue up here. So I get x to the 6th u prime is equal to c1. Okay, so then I'm going to get u prime is equal to c1 x to the negative 6th, and I'm going to integrate. So I will get u is equal to negative 1/5 x to the negative 5th times some constant c1, and then I have a constant c2. And now we're going to need to do some substituting again. If we recall, we defined our y to be u of x times x to the 3rd. So here is our u of x. So then we're going to find that y is negative 1/5 x to the negative 5th times some constant c1, add c2, all of that multiplied by x to the 3rd. So we get our y then to be negative 1/5 x to the negative 2nd times our constant c1, add c2 x to the 3rd. Okay, so let's do a quick reminder of what we were trying to do. We were trying to find a second solution. So we have to think back to superposition. If we remember back to the superposition principle says that if we have two linearly independent solutions, we can construct another solution as the sum of multiples of the two solutions. So we had y1 was equal to x to the 3rd, that's that solution, which means our second solution comes from here. Now that negative 1/5 and the c1, that's just a constant. So what we care about is that x to the negative 2. So this is our new solution. Now, fun fact, you can show this if you want, I'm not going to. These two solutions are going to be linearly independent. Okay, so now you've seen the general process of reduction of order. Before we go to the more general case, we're going to do one more example just to make sure that we have this process down. So here's our second example. We have that linear equation that's homogeneous, and we have our known solution, which is y1 is equal to e to the x. Again, notice that this is a homogeneous equation, so reduction of order will work for homogeneous equations, not non-homogeneous. Now you have two options here. If you want to pause the video and try this one on your own, I think that's a great idea. If you want to just look with me or go through it with me, you certainly can. So first thing that we are going to do is we're going to define y to be u of x times e to the x. Ultimately, we're going to need to go back to our equation. So we're going to need y prime and we'll need y double prime. So we get u e to the x, add u prime e to the x. And just remember, I'm being a little lazy with my notation here. U and u prime, those are both functions of x. So then our y double prime will be u e to the x, add u prime e to the x, add u prime e to the x, add u double prime e to the x. So then, combining like terms and simplifying, I get u e to the x, add 2u prime e to the x, add u double prime e to the x. Okay, if you've gotten this far with me, again, feel free to pause the video and try this one on your own if you're confident. If you don't feel like it or you're not confident, just keep sticking with me. So now we're going to go back to our differential equation. So our u double prime subtract u is equal to 0. So So we get u e to the x, add 2u prime e to the x, add u double prime e to the x, subtract u e to the x is equal to 0. And what we should notice is we have some terms that subtract out, leaving us with 2u prime e to the x, add u double prime e to the x is equal to 0. Now e to the x, I'm going to just divide that out. So I get 2u prime, add u double prime is equal to 0. Okay, so now we're going to substitute again. At this point, we're going to let w be equal to u prime. So then dw, or w prime, is equal to u double prime. So that's what we're going to substitute in. So now we get 2w, add w prime is equal to 0. Or it can be written as w prime, add 2w is equal to 0. This is what we're going to solve. So again, linear or separable. I'm going to treat it as a linear equation. So my integrating factor then is going to be e to the integral of 2 dx, which is just e to the 2x. So when I multiply my equation then by e to the 2x, the left side is going to be the derivative of the product of w and e to the 2x. So integrating, we have w multiplied by e to the 2x is some constant. So we get our w then to be c1 e to the negative 2x. And now we're going to remember what that w is, and that's what we're going to substitute in. So we get u prime is equal to c1 e to the negative 2x. So I'm going to integrate. So I get u is equal to negative 1/2 c1 e to the negative 2x, add some second constant. And then if we recall from the beginning, we defined y to be u of x times e to the x. So substituting in this u we just found, we get our y to be negative 1/2 c1 e to the negative 2x, add c2, all of that multiplied by e to the x. So simplifying, that becomes negative 1/2 c1 e to the negative x, add c2 e to the x. Okay, and so if we recall reading this again, we do not care about these constants. What we care about is these two functions. E to the x is that first solution that we already knew, which means this is our second solution. So our second solution is e to the negative x. And again, remember that these two solutions are going to be linearly independent. Okay, so at this point, hopefully your brain is churning and you're thinking about why this would be helpful or where we're going with this. Now remember, our whole goal for solving these linear differential equations, whether they're homogeneous or non-homogeneous, is to find the general solution. Well, the general solution is going to be a linear combination of linearly independent solutions. So if we can find our linearly independent solutions, ultimately we're going to be building then to form the general solution. So what we're going to do next is take a look at the general case. So general case, do we have to go through this reduction of order process every time, or can we find a little bit of a rule? So let's say that we have this differential equation right here that is second order, it's linear, it's homogeneous, and if you're going to notice, the lead coefficient is 1. And let's say that we have some solution y1 of x. So what we're going to do right now is we're going to go through the reduction of order process with this general equation and that general known solution y1. So we're going to allow y then to be u of x times y1 of x, which means our y prime is going to be u times y1 prime, add u prime times y1. Taking the derivative again to get the second derivative, we get u times y1 double prime, add 2 y1 prime u prime, add y1 u double prime. So all I did is I differentiated, but then I combined the like terms because we know about what we're going to get. If we return back to our equation, so our y double prime, add p of x times y prime, add q of x times y is equal to 0. And we substitute in our y and our y double prime. We're going to get u y1 double prime, add 2 y1 prime, u prime, add y1 u double prime, add p times u y1 prime, add y1 u prime, add q times u y1. And we know that that's equal to 0. Okay, so ultimately what I want to do then is I have u prime, and I have u double prime. So I'm going to need to do a little bit of factoring. So I'm going to change this so that I have u multiplied by something, u prime multiplied by something, u double prime multiplied by something is equal to 0. Okay, so doing some factoring and some moving around, we're going to get y1 double prime, add p of y1 prime, add q of y1, and then we get 2 y1 prime, add p of y1, and then we just get y1. Okay, so at this point we should be thinking, what are we doing here? Is there anything helpful? Well, maybe that you notice that this looks very familiar. It looks like our original equation. So that is our original equation with the known solution plugged in, which means all of that factor is equal to 0. Okay, so that makes our equation look a little bit nicer. We're now just left with this part of the equation. So putting the y double prime first, I get y1 u double prime, the u double prime first, not the y. And then we get 2 y1 prime, add p of y1 u prime is equal to 0. Okay, so what I'm going to do next is I'm going to divide out that y1. So I have a lead coefficient of 1. So this gives me u double prime, add 2 y1 prime, add p of y1, all over y1 times u prime is equal to 0. And now we're at the point where we're going to substitute again. So we are going to let w be equal to u prime. So then w prime is equal to u double prime. So this becomes then w prime, add 2 y1 prime over y1 plus p times w is equal to 0. Okay, and so now again, linear equation, or we could solve by separation, either one. Because we've been doing linear, we're going to keep going with that. Okay, so our mu then, our integrating factor, is e to the integral of 2 y1 prime over y1 plus p dx. Okay, here's where we need to be a little bit careful because our notation was poor. So I'm going to have us recall that y1 is a function of x and that p is a function of x. So we just need to recall that for when we do our differentiating, or our integrating rather. Okay, so this then will become e to the 2 natural log of y1, add the integral of p of x dx, which is really e to the 2 natural log of y1 multiplied by e to the integral of p of x dx, which ends up being y1 squared e to the integral of p of x dx. Okay, so that integrating factor, we're now going to return back here. And when we multiply by that integrating factor, we remember that the left side ends up being the product of w and that y1 squared e to the natural log of p of x dx. So it's the derivative of that product. Integrating then, we're going to get w times y1 squared e to the integral of p of x dx is equal to c1. So our W will be C1 times e to the negative integral of p of x dx over y1 squared. Doing some more substituting, W we defined as u prime. So if we integrate that, we are going to get u then is equal to C1, the integral of that e to the negative integral of p of x dx over y1 squared, integrating with respect to x, plus C2. Okay, almost done. So our y is u of x times y1 of x. So we get our y then to be C1 times y1 of x times the integral of e to the negative integral of p of x dx over y1 squared plus C2 times y1 of x. Whew. Okay, and last thing we got to do is interpret this. This is our known first solution. So then if we look here, we don't care about that constant, which tells us that our second solution y2 is equal to y1 of x times the integral of e to the negative integral of p of x dx, all of that over y1 squared dx. Yeah, so I guess my expression was missing a dx there. So this is the general form of the second solution. Okay, so now that we have this general form of the second solution, let's take a look at an example using it. Okay, so here we go. Example 3, for x is greater than 0, that equation has a known solution, y1 is equal to x. We are finding y2. Just to help so you don't have to keep changing back and forth, here is what I have written from the previous page of our known second solution. First thing that I want us to notice is that we have a lead coefficient of x squared. So we are not yet in a form where we can use our formula off to the right. We're going to have to start by dividing by x squared. So our equation then becomes y double prime, add 2 over x y prime, subtract 2 over x squared times y is equal to 0. Now we can use our formula. So our second solution is going to be our first solution, which is x, multiplied by the integral of e to the negative integral of 2 over x dx over x squared. Okay, so I'm going to have to start with that integrating, the initial integrating. So I get e to the negative 2 natural log of x over x squared dx. So that will give us x multiplied by the integral of x to the negative second over x squared dx. So this is x multiplied by the integral of x to the negative fourth dx. So this is x times negative 1/3 x to the negative third plus c, but we don't care about that constant. So this is negative 1/3 x to the negative second. Again, don't care about that constant. Now for our second solution, we don't care about this constant either. So our second solution is x to the negative second. So there we go, a little bit quicker than those first two examples that we did. A note for you, your homework has both reduction of order and this shortcut. You need to be able to do both. So you need to be able to do reduction of order. You also need to be able to do this quote unquote shortcut. Okay, so I've said this a few times, but I want to remind us that all of these reduction of order problems that we've been doing so far apply to homogeneous linear differential equations. And so the question, of course, is what happens if the equation is non-homogeneous? And so let's take a look at these few last notes down at the bottom. So what happens if you have a non-homogeneous linear differential equation? Unfortunately, we cannot use that shortcut or that formula above, but you do have to do the entire reduction of order process. So then when you get to step 3, though, you are going to set your expression equal to the regular equation. What I mean by that is, since it's non-homogeneous, your equation is not going to equal 0, it's going to equal something else. And then you'll solve. You're going to get a solution of the form complementary, add particular. And just to remind you, your particular solution has no arbitrary parameters. So there's no C in it, whereas your complementary solution will have arbitrary parameters. You do have 1 or 2 like this on your homework, so make sure you give them a try. Thank you for sticking with me. That was reduction of order. Looking forward, what we're going to be doing, in this video you were given a solution. Well, what happens if you have a linear, homogeneous, or non-homogeneous differential equation? How do you solve it if you aren't given a solution first? So until next time, thanks for sticking with me.